All right, great. Okay, so welcome everyone to today's talk on diffusion models. So it's my great pleasure to introduce you Arash Vahdat. So Arash is currently a principal research scientist at Nvidia Research, specializing in generative AI technologies. Okay, so he has done a lot of amazing works in diffusion models, and I believe he is one of the leading researchers right now, not only in India, but also basically in the field. Okay, so even before diffusion models became cool, he also did something very interesting that tries to revive hierarchical VAEs in terms of making them generating great images. So that was the work that made me hopeful again in terms of this VAE stuff. Yeah, so today Arash is going to give us a talk that tries to overview his research efforts so far on diffusion models. So yeah, back to you.
Yeah, thanks for the introduction, and thanks for having me again today. And I know it's Friday evening on your side, so hopefully I won't keep you too long, and you can start your Friday before I start my Friday morning, before I start working. Yeah, so today I'm going to talk a lot about denoising diffusion models. And as Imogen said, I started with VAEs and some like energy-based models before starting to work on diffusion models. And I think when diffusion models kind of came out again into 2020, I was one of the first people to realize that at Nvidia, I was one of the first people to realize, oh, these models are really strong and they're fixing some of the issues that other generative models, like fluid-based generative models, like VAEs and energy-based models have. So let's get started. Sorry. Okay. So I'm pretty sure, like most of you, all of you know generative learning. So let's just remind ourselves, in generative learning, what we assume that we have a collection of samples from a data distribution. Here I'm showing you data distributions like images of cats. So the samples are just some images drawn from.
You know what? When you
sorry. Okay. Thanks. So we have samples drawn from a distribution of cats, and then what we want to do, we want to use these samples to train a neural network. And if everything goes well, if our neural network, which is a deep generative model, captures the data distribution properly at the test time, we can now start drawing samples from this trained model. And if everything goes smoothly, we're going to be able to generate these like cute, good-looking cats at the test time. If you were on internet, it was probably very hard for you to not realize all the excitement around some of the models that were created using diffusion models. DALL-E 2 and Imagine are two good examples that came out last year that showed really good capabilities in terms of text-to-image generation. And diffusion models are basically kind of, it's getting there, starting to be a bit old, but they came around 2020, and they showed very promising results, at least in terms of image generation, outperforming some of the GAN state-of-the-art GAN frameworks around that time. So today, what I'm going to do, I'm going to very briefly introduce diffusion models, and I'm pretty sure most of you don't need this. I just want to remind us about diffusion models and highlight some of the recent projects we did at Nvidia using diffusion models. And after that, I will dive deeper into some of the methods we developed early on accelerating diffusion models. And I'm going to talk about three specific works. First one is latent score-based models that later became known as latent diffusion models, denoising diffusion GANs, and higher order solvers for diffusion models. So let's get started with denoising diffusion models. By the way, feel free to ask me any questions. I like to keep it interactive. If you have any questions, just let me know. Denoising diffusion models, which are also known as score-based generative models, these are not really very different. They are almost the same. They consist of two processes. A forward process that starts from image and adds noise gradually to image or input, such that eventually you get white noise. So here I'm using the image of my cat, Peanut. We start from this image and we start adding noise gradually, iteratively, such that eventually we get to some known distribution. Here is usually Gaussian noise. And then this is a forward process, a very simple process. It's almost fixed. We don't need to train anything for forward process most of the time. But what is interesting is the reverse process. Reverse process formulated in the reverse direction, where you start from noise and you train a neural network to denoise input images. So the reverse process is just a denoising model that takes noisy images and denoises them one step at a time. And what happens is that now, by training a denoising model, you can actually now have a generative model that would start from noise and generate data by gradually denoising it. So if we dive a bit deeper into formally how these forward and reverse process are formulated, the forward process takes a very simple Markov process with this Gaussian diffusion kernel, right? In each step, we take previous step, like we take the previous noisy image here, that for example, xt-1, and we form a distribution on the next step using this Gaussian distribution. And this takes a very simple form. Its mean is basically same as the previous image that is rescaled with this quantity here. This is just a scalar quantity that rescales. And then we have this noise injection, this variance of noise that is injected to the data. Think of beta t as a very small scalar value that represents like the variance of the noise that is being added. Basically, at every step, we take this xt-1, we scale it down tiny bit with this square root of 1 minus beta t, and we add a bit of noise. And the next time we scale it down and we added a bit of noise. This process is known as variance preserving process, because if your input had a normal, standard normal distribution, this wouldn't change, this diffusion kernel wouldn't change the distribution. So it would be, the distribution of samples would stay the standard normal distribution. And the reverse process is very similarly defined by a Markov process that works backward. At every step, you take noisy instance xt and you try to predict less noisy version of that instance. And the way we parameterize this normal distribution, we have this trainable mean and some fixed variance. So we usually don't need to necessarily train this. We can just most of the time you can use the same variance that was used in the forward process and the reverse process as well. The trickiest part is this mean that represent the mean of less noisy images given the noisier images. And usually we use a neural network to represent this. This is the main trainable component. It's implemented using some UNet or some denoising autoencoder that takes noisy image and predicts the average of less noisy versions. So in simple words, basically you have this like forward Markov process that adds noise, and a reverse Markov process using normal distribution in each step that learns to denoise. And the main component is this denoising model that takes noisy images and predicts less noisy version of them. In a seminal work by Yang Song et al. At ICLR 2021, the authors showed that actually these processes also can be represented using stochastic differential equations or some form of Langevin dynamics that start from samples from data distribution. In the forward process, you start from samples from data distribution and you walk toward a known distribution. And usually this is some standard normal distribution, for example, right? So the forward process can be represented as a particular SDE or stochastic differential equation, and the reverse process can be also represented as another SDE that starts from a known distribution, Gaussian distribution, and walks back towards data distribution. This reverse process consists of two terms. This is like a SDE describing the reverse process. We have this drift term and this diffusion term. Diffusion term is a simple, the standard linear process. The drift term here, what's interesting, it requires estimating the score function or the logarithmic derivative of the data distribution at time step t, right? This is what we mean by score function. And usually you can show that actually mathematically, this is basically the same thing, almost same thing as the denoising model that we were learning in the previous step. So by learning a denoising model, you're basically learning this score function. The moment you have that denoising model, you can just plug it into this SDE and start generating samples by solving this reverse SDE. I don't think you necessarily need a deeper tutorial on diffusion models, but if you have junior students or someone who's picking up this space, we did a tutorial at CVPR last year that got some attention, and a lot of people used this when they were starting their journey in this space. So if you like to check some tutorial, or if you know someone who needs this, feel free to share them this tutorial, and we're gonna actually we do something similar this year at CVPR again, and we're hoping that we can do again another review of diffusion models and what happened in the field in the past 1 year or so. So with that in mind, let me start with just giving some overview of some of the recent works we did at Nvidia. Of course, this doesn't capture all the exciting things that are happening at Nvidia. I've been just involved in a few projects in the last few years that I want to cover here, but there's just so many other things happening, like in terms of like 3D modeling, text modeling, and image video modeling using diffusion models, for example. And I'm going to just touch upon a few of them. So one of the things that we observed early on when we started working on diffusion model was that we realized that there is a very nice trade-off between content versus detail generation diffusion models. You can actually mathematically show that in the forward process, as you go, like if you start from image and you add noise, you initially just perturb mostly the high frequency content of the images. Like when you add noise, a little bit noise, it first only perturbs the high frequency content, which corresponds to very low level details in images. And later on in the forward process, when you inject a ton of noise, that's the time when you start perturbing the low frequency content, which represents really, coarse content in images. As a result, in the reverse process, when you're generating data, you also first start generating the coarse content, the global high-level content, and gradually towards the end of the process, the time when you start generating very low-level, high-frequency content. This is one of the reasons why when we are training diffusion models, the weighting of the training objectives is very tricky, because you have a shared model across these time steps. This weighting actually helps you trade sometimes low-level details for better representation of these coarse high-level details. So motivated by this, we actually realized that when we are training also diffusion models for text-to-image models, right, for text-to-image modeling, the diffusion model has a different behavior in the course of the denoising process, right? Early on, the input image contains mostly noise. So it's very tricky for the neural network, the denoising model, to know which direction it needs to go to denoise the image. So in that early stages of the denoising, what happens is that your neural network, your denoising model, actually uses the text input a lot to figure out which direction it needs to denoise the image, right? But as you move forward in the denoising process, when you have some content in your in the visual space, when your image has some visual content, then the denoising model starts ignoring the text input and mostly relies on visual content to denoise. So there is a very nice trade-off between where to use text and where to use visual content in the course of the generation in the text-to-image models. So inspired by this, we introduced Edify, which is an ensemble of diffusion models for image generation that uses different denoising at each time step, not at each time, at each interval of time. So we split this time interval, this horizon in the denoising process, into multiple intervals, and we use different networks to represent the denoising model. The nice thing about this is that now you let different denoisers become specialized for different time intervals when you're denoising. This increases the expressivity of your model, because you just simply increase now, number of parameters, basically the expressivity the neural network will have. However, this doesn't change actually the sampling time, because if you have a fixed discretization, if you use a certain number of sampling steps at the test time, you have to call a certain number of neural networks. And now it's, in our case, you just call different neural networks, whereas in the standard case, usually you just share that network and you call the same network over and over during the course of the image. So this was a very nice trick to increase the expressivity without actually increasing the sampling time necessarily, because this has the same network architecture. So using Edify, we could actually generate these cute dogs where they, on their t-shirt, they say Nvidia rocks, which is something that we believe. This model showed better representation of text when we were generating images with some like text on them. We also could generate these nice cats that are riding their scooter and they have helmets. And it was really exciting. This was like the framework that we introduced in November. We released the paper last year in November. If you have any questions, I'm going to do a few like projects. If you have any questions about this, let me know. Otherwise, I'll gradually move to the next one. So another work that we did is I'm going to talk about latent diffusion models, but before talking about that, I want to say one of the works we did was we used latent diffusion models to learn distribution over point clouds. Point clouds are just the most primitive way of representing shapes, 3D shapes. And we also showed that after generating point clouds, you can actually reconstruct meshes on top of those point clouds and get these very nice, good-looking 3D shapes using our model. The nice thing about this work was that because it uses a very expressive latent diffusion model, we were one of the first ones that trained this model on all 55 categories of shape. That usually folks who work on shape, they use very few categories, like 1 or 2 categories like chairs or cars. But this time we just trained this model in an unconditional setting on all 55 categories, and we sampled actually it does a very good job of representing categories in this, like good quality samples from these categories on ShapeNet. One of other observations that we had was that many of the text-to-image models in the literature, they use cross-attention to inject text into the diffusion model. So this is an example from the latent diffusion model paper by Rombach et al. At CVPR 2022. They had this the idea that they were using UNet for representing the denoising diffusion model, but they were injecting all the conditionings, including text conditioning, using cross-attention. What happens here is that when you now inject text information using this cross-attention, your visual features in that UNet will start being correlated with the text representation, right? So you keep at every layer almost, you have this attention happening between visual features and the text features. So this will make your internal representation highly correlated with text features. What this means, it means now your internal UNet representation has rich semantics, because text features usually have rich semantics. It's natural language, right? So this is the language we use for describing objects and stuff. So when you correlate the visual features with these text features, you're going to have a model where its internal representation has very nice semantics in it. So motivated by this, we were questioning ourselves, can we use pre-trained diffusion models now, not for generation, but for downstream segmentation, right? Can we do segmentation using just pre-trained text-to-image models? And we want to be ambitious. We want to see, can we do open vocabulary segmentation? And open vocabulary means that you basically don't know which categories you will be segmenting at the test time. You want to be able to take any new categories and segment them. So our idea was very simple. We said, okay, let's just extract representation from a text-to-image model. So we're going to just go to UNet architecture of that text-to-image model. We're going to extract features from this pre-trained model. Because these are text-to-image models, they're also conditional on some text, right? But we don't want to necessarily assume that we have images and text at the same time. What we're going to do, we want to apply these segmentation models on images. So we just said, let's just take the image and come up with some, implicit captioner that would caption this image. This implicit caption, you can think of it just like something like clip image encoder that takes an image, maps it to some nice semantically meaningful space, and then you use some MLP to extract some implicit text embedding that is fed to this unit. This is just a trick. Like you can just almost ignore this. This is just some trick to extract some implicit text encoding. Now that you have this, you can just pass the image and the text embedding to the unit, the denoising text-to-image diffusion unit, and extract representation from these intermediate layers of the unit. Now, what we did after this, we just gave this to a simple segmentation model, mask that generates masks and embeddings from these masks. So you can think of like it uses these convolutional features, extract some masks as well as some representation of each one of masks. Now, in order to learn the segmentation, well, all you need to do, you need to just supervise these masks. So on a data set that it has segmentations and labels, we're going to now just supervise those binary masks. We also need to supervise the features exactly on those masks so that later on we can assign classes to them, right? So in order to do that, usually classification of regions, what you usually do, you use cross-entropy loss. But here, because we want to do open vocabulary for that classification of regions, what you can do, you can actually take these categories that you have in the training set, you use text encoder to map it to the same space of text, and use the text encoding of categories to perform this classification. The reason why we want to do this is because of two things. One, these features are correlated with the text encoder, the text representation. So it will make it easier for us to classify now these regions using just text encoding of the categories. And the second, if you use text encoding at the test time, now you can enter new categories and your model will just use the text encoding of those categories to do segmentation. So this enables us to do open vocabulary. So here I will show you some examples. This video shows us sorry, this has audio. So this has some music on it, so I cannot hear you if you speak at this point. So one of the other things that we were interested in using diffusion models was for adversarial defense. So this example I'm showing here is famous in the adversarial defense literature. Here you have this image of panda where its pixel intensity are like adversarially perturbed, such that if you give it to a classifier, it will not be able to classify it as a panda. So what we want to do, we want to see if we can take an adversarial image and we just add a bit of noise, right, by following the forward process in diffusion models. So if you do this, you basically now combine all these like little adversarial perturbation in the pixel intensities with some white noise, right, that is injected. But now we can follow the reverse process to remove all the injected noise and perturbations. What we are hoping is that by just simply adding noise and denoising it using the reverse process, you will be able to wash out all these like tiny perturbations on the image content that are forming this adversarial attack. So this is a very simple idea that uses just a generative model to purify images, right? So that's why we call it diffusion models for adversarial purification. And the nice thing about this is that this process is not aware of what kind of attack you have at the test time. It's not also dependent on a particular classification model, right? It just uses a generative model to simply like add noise and then remove it. And by doing this process, it tries to remove any adversarial perturbations. We call this method diffpure, that takes adversarial images and just tries to purify them by this technique. And then now that we get these purified images, we can pass them to classifier and hopefully get correct categories. However, in the adversarial training community, any moment that you have a defense mechanism, you actually need to have attack mechanism. You need to show how you can potentially attack this. So usually, in order to do attack, you need end-to-end attack. Like you want to be able to have a adversarial attack mechanism that will be able to, for example, have greatness backpropagate through the whole classifier and the defense mechanism. So in this work, we showed that actually you can easily backpropagate through this generative SDE by just backpropagating through SDE. There's some recent literature that showed that you can basically backpropagate through SDEs and get the derivative output with respect to input. So using this, we showed that we can actually do end-to-end attack to this model. I'm going to show you some examples here. On the left side, you see these examples from CelebA dataset, where we have created these like adversarially perturbed images. So for example, this is a smiling category, and we have adversarially, I think, perturbed them to be classified as eyeglasses, if I remember correctly. And this is other way around. This is eyeglass, and we're trying to perturb them for smiling. So what here we have increased the level of adversarial perturbations so that's visible to us. So you can see that there are some like visible perturbation on the image that tricks the classifier. In this column, you see what happens when we add noise, and then what happens as we are denoising, right? So this is halfway through, and this is all the way after we completely denoise the image using the reverse process. And you can see how the denoising process got rid of all these like adversarial perturbations and made images very similar to clean versions of those images. And this is basically the way that we do. We just add noise and denoise, and the output we pass it to classifier. And we hope that using this, we will be able to get rid of all the adversarial perturbations. As I said earlier, the nice thing about this technique is that it's not attack dependent. You're not training a model for a particular attack. And also it's not downstream classification model dependent. You're not training a classification model to be adversarially robust. You are actually just using a generative model. So in this chart, I'm comparing our method against some of the models in the literature, some of the state-of-the-art models in the literature that are designed for unseen threat models. So these models, similar to us, they don't know what kind of attack will be used at the test time. And you can see that these diffusion models, by a large margin, outperform the prior works on this space. It's really exciting to see that now generative models can actually help us with getting rid of the adversarial perturbations in images. So this actually created some exciting follow-ups in the community, the adversarial robustness community, and there were a few of other follow-up works that show that these denoising models and diffusion models in general can be used for gaining robustness against adversarial attacks. So this might be a good time to stop here and let you, if you have any questions about the first part of talk before I dive deep to the second part. If you have any questions, let me know.
Okay, so I have one question. So yeah, I've looked at this adversarial robustness of purification with generative models as well, right? And people previously have also debunked these ideas in terms of using, say, pixel VAE or GANs, right? Yeah. So would you say that currently these things works because of the properties of diffusion models, or because you scale up these models to make it generate really great images? Basically just asking that whether, by having, let's say, bigger models, can we somehow also revive, let's say, GANs or pixel VAEs to do this?
So it's a funny story about this work is that actually when we started doing this, originally the idea was to use GANs. which is, it was around the time that diffusion models were like around 2021. So we didn't have a lot of success actually with the GANs when we were doing it, and we were using some of the best GANs out there. So I think having strong generative models, of course, one of the reasons, like these diffusion models we're using here are very good. They generate very high quality images, right? The other, I think, aspect that makes it really well suited for diffusion model is the fact that these models are trained by adding noise and denoising, right? You're basically learning a denoising model, and this process of forward process allows you to, get rid of these high frequency, perturbations without changing the content much, right? So it actually also suits really well to diffusion processes to add a bit of noise and remove it. I think there's a possibility that if we have really other forms of strong generative model, especially like VAEs, we might be able to do this well. I don't have a lot of hope for GANs because they're not necessarily, they have like sometimes mode coverage issues. So if you give this image to GAN, you may not be able to find a latent encoding that would represent this image. Sometimes this GAN inversion becomes a problem. So we have this kind of issues with GANs, like finding a latent encoding of images at the test time wasn't that easy.
Okay, yeah, thanks. Any questions from the audience? Well, I guess if not, we can carry on.
Yeah, sure. So in the second part of the talk, I want to delve a bit deeper into some of the works we did on accelerating diffusion models. Remember that earlier I was telling you that this work by Yang Song at ICLR 2021 showed that you can actually describe diffusion models using stochastic differential equations. These stochastic differential equations, you can think of like some form of random walk that map data distribution to some known distribution. The problem here is that in one side you have this very simple distribution, which is often normal, and on the other side you have this very highly multimodal complex distribution. You can imagine that the SDEs that will start mapping this noise distribution to data distribution, they will have a very complex dynamics over time. And this complex basically function that you're integrating over time makes it really hard to sample from these models. So you're going to solve these SDEs numerically, right? So if you have a function that has a very complex dynamics, if you want to solve the SDE, you're going to actually need many number of steps to be able to solve these functions accurately. This is one of the reasons why some of the early works in this space had to use thousands of steps. Over time, of course, more and more solvers came up, and I'm going to talk about some of these things. But it's just that this temporal dynamic can be really complex, and that's one of the reasons why we need many number of iterations to solve these sampling SDEs, or sometimes ODEs. So when we start working on diffusion models, we realized that actually there are 3 criteria that generative models cannot satisfy all at the same time. These criteria include fast sampling, sample quality, high quality sampling, and as well as mode coverage or diversity. If you look at GANs, they do very good quality sample generation. They're also often very fast. However, as we know, their training causes mode dropping, and they cannot represent the diversity in the training data distribution really well. And then on the other side, we have livelihood-based models that they do a very good job in representing diversity in the data distribution. They're also often fast, but most of the times, at least for image generation, they sacrifice sample quality. They have a hard time generating very high quality samples. And then on the other side, you have diffusion models that they have very good mode coverage, and they have very high quality sample generation, but they're very slow to sample from. So we call this this problem, this issue in generative learning as a generative learning trilemma, meaning that there is no model that can address all 3 of them at the same time, at least for image generation. So we task ourselves with how can we tackle this process by this problem, all 3 criteria at the same time, by hopefully accelerating diffusion models. If you can accelerate diffusion models and keep these two nice properties of diversity and sample quality, you actually now have a generative model that's fast. It has also these other nice features of diversity and quality. So I'm going to talk about 3 works that we did in this space. And the first one is score-based generative modeling in latent space. We had at Nourish 2021, we had this idea that can we just move, instead of training diffusion on the data space, can we move to latent space? So the basic idea is to use something like a VAE to map data space to some latent space. So our VAE will include encoder that takes images and maps them to some latent space with some encoder, and some decoder that takes latent embedding of data and learns to decode. And what we're going to now do is we're going to assume that our prior is represented with the diffusion model or score-based model. And we're going to use diffusion model to represent the distribution of the latent encodings of the data. So it's a very simple idea. Use VAE to encode and decode the data, and use a diffusion model to represent the distribution of encodings. So the reason why we want to do this, we actually envisioned very early on that there are at least 3 advantages of doing this. And the first advantage is that, remember I was telling you the data distribution is very complex. But when you use a VAE to map data samples to latent space, you train this VAE with a normal prior. What this means that you actually take a data distribution and you map it to a space where the distribution of latent encodings is as close as possible to normal distribution. If it was perfectly normal, we were done. We would be using VAEs for everything. Usually what happens is that you bring the distribution close to normal, but there's always some gap. Now, what diffusion model will do, it will learn that gap. Like, how can you take this distribution of latent embeddings that is almost close to normal, but now map it to perfectly normal and learn to undo that, right? So, because the distribution of latent embeddings is very smooth, very close to normal, what happens is that these processes that are formed in the latent space will end up being very simple processes. These are going to be functions that are very smooth. And if you have a function that is smooth, it's going to be easier to actually solve the ST or ODE using those smooth functions. So if you're solving a ST that is smooth, you can actually take very large denoising steps. You won't need many functional evaluations. So this was one of the main reasons why we wanted to go to latent space. The distribution of samples in the latent space would be simpler. As a result, these STEs would be also easier to solve. The second reason why we want to go to latent space was that it's known that if you add additional dimensions to your data, you actually increase the expressivity of your generative model. So by introducing these latent variables, we actually have now more expressivity in our framework. It also brings some more flexibility. I will come back to the question. It gives us also more flexibility because you take these images that are high resolution, you can map them to low resolution, especially low resolution, right? So the networks that you will use don't need to be very deep, for example. Because you have especially low resolution, you don't need many layers. And finally, this actually allows us to apply diffusion models to some type of data like graphs or text or 3D data that are harder to represent using some like in continuous space. So these diffusion models assume that your data lies on some like fixed dimensional continuous space. But if you have some data like graph or text, as long as you can encode, decode your data, you can now fit diffusion models in the latent embedding of that kind of data. So it also allows you to apply to other applications. Yeah.
Hi, Arash. So there's a question. Okay, so yeah, unmute yourself.
I was just about to stop actually. Yes.
Okay. Do we need a very expressive encoder and decoder here? Because we want that we just use a very simple encoder and decoder here, like just a linear mapping, and then we can learn very say meaningful lateral representation by the diffusion model. So I'm really curious about whether we need a very powerful encoder decoder to learn a good mapping, or we just need a very simple encoder and decoder to and using a very simple encoder and decoder, we can also learn very meaningful mapping here.
Yeah. So so we use very strong encoder decoder. So we use NVAE with the hierarchical structure and stuff. I think what happens when you do something like that is that you can bring it closer and closer to normal distribution. That means you have very expressive encoder, it's more likely that you bring it to closer to normal distribution. And what this means is that it's actually the dynamic in the latent space will be much simpler, you know, if you make it very close to normal distribution. You probably know that, like, after this work, latent diffusion models came out 9 months after this work, where they used simpler encoder decoder. So they did not have a hierarchical structure. And their view was, we just want to compress the data. We want to just go to some very low dimensional latent space. And that doesn't guarantee smoothness in the latent space, but because it's low dimensional, training, but what we learned later was that because they have much lower dimensional latent space, it's easier to train the diffusion model.
Yeah, I think this thing is quite weird because that we want, if you use a very very powerful encoder, that means the diffusion model is very easy to learn, right? So we lose the power of the diffusion model. But
we don't lose. No, we don't lose. I mean, what happens is that what happened to us was that the dimensionality of latent space was very big, and it was very hard to learn the denoising model in that space.
Okay, yeah, that's what I want to say. Yeah, it's hopefully we can use a very simple encoder and just use the encoder to reduce your dimension and use the power of diffusion model to learn a very meaningful latent representation. Yeah. Okay.
So I think there was exactly. I think one of the what we were following was more like, you know, this variational mindset that if you increase the dimensionality, you introduce expressivity. But in the inside, we didn't realize that when the dimensionality of data is huge in the latent space, this actually makes training the denoising model, especially with denoising score matching, becomes harder.
Okay, thanks.
Yes, thanks. I see another show of hand.
Yeah, I have a following up question. You said that the distribution of latent impeding is close to the normal distribution. So I'm wondering if there is any constraint to achieve that goal, or how to ensure that it's close to the normal distribution.
That's a good question. So is there any quantitative experiment to show that? Is that what you're saying, or like you said, clustering?
Maybe are there any like training objectives or something explicitly constrained that their latent embeddings are close to this normal distribution?
Yeah. So when you train VAEs with the standard normal prior, you know, you can show that this basically encourages the distribution of latent embeddings, like aggregate posterior distribution, to be as close as possible to normal. You know, like you're basically bringing the embeddings close to normal. So the way we train this model, we first pre-train the model VAE with a normal prior, and then we kick in the remaining training, which is end-to-end, including both VAE and the prior at the same time. After pre-training. So you can show that actually training VAE with standard normal prior would bring the distribution of the embeddings closer to normal.
Okay, I got it. Thank you.
And both is clear. I think we discussed in the paper. I think somewhere we discussed this too. So very briefly, I wanted to mention how we train these models. Right? So for training this model now, we can just use variational lower bound to train this objective. You probably very familiar with variational lower bound. It consists of reconstruction loss and KL loss. You can just now keep the reconstruction loss, decompose the KL loss into entropy and cross entropy term. What happens is in this framework, these two terms, reconstruction loss and entropy of encoder, these are just, you can approximate them very similarly to how you do it with VAEs. Like you can approximate these terms with your parameterization really easily. The trickiest part is this cross entropy term, where you basically want to be able to optimize this with respect to both encoding distribution as well as prior. So one of the technical novelties we had here was we came up with a very simple cross-entropy expression for when you have this like encoding distribution and you have diffusion as prior. And also we came up with some very simple techniques to reduce the variance of this term when you would use Monte Carlo estimate. So very briefly, I will just show you the expression. So the cross-entropy, the expression we came up with, it's basically some reweighting of the denoising score matching objective. So we basically showed that with some particular weighting, if you just form the denoising score matching objective and you optimize that with respect to both Q and P, you would be optimizing cross-entropy loss, which was really interesting. So this is basically, you have this expectation over time here. You have this like forward diffusion in the latent space. You have this denoising basically score function. So you have this like the diffusion kernel and the score function of that. And then you have this trainable prior here. And here you have just a constant that you can ignore it because it does not depend on Q or P in general. And this simple expression is very helpful for training now both encoder and prior at the same time. So using this technique, we got some good results on some of the standard benchmarks like CFAR10, CelebHQ, and MNIST dataset. And this is the latent interpolation in the latent space. So you basically, I'm walking in the latent space. This is the this is basically the base distribution of the diffusion process in the latent space. So we're walking in the latent space. We denoise these latent variables to get the encoding, and then we decode them to get these images. And you can see that this technique generates very high quality images. And sometimes what's interesting is that you see very sharp, especially on CFAR10, you see very sharp transition. Go back and you see very sharp transition sometimes between categories. And this basically shows how expressive diffusion models are. They can just, because the data distribution consists of islands here, it just jumps from one island to another very rapidly. So this is how the samples would look like as we're solving the denoising process in the latent space. So here, just on the left side, we have just the base distribution, and this is how it looks like as we're solving the reverse process. As you can see, the artifacts on the images don't contain any noise, right? Because we keep decoding everything in the latent space. The artifacts are different. You can basically show that what you are doing when you do diffusion process in the latent space, you actually define a nonlinear process in the data space. You can mathematically show that latent space diffusion model is some form of nonlinear diffusion process in the data space. And so just to summarize, if you need to know more about this work, you can actually check this website. You'll search for LSGM, a latent score-based generative model. So the basic idea was to formulate diffusion models or score-based generative models in the latent space. One of the main goals was to accelerate sampling, and we actually saw with the success of latent diffusion model and stable diffusion, we actually saw that actually these models can be really good in terms of learning generative models. There was a work by Chen Mei et al. I think it's going to appear at CVPR to my understanding, that they showed that actually you can accelerate latent diffusion models and you can get actually sampling, high quality sampling in 2 steps, which again shows that basically latent diffusion models are easier to accelerate. And as I said, one of our main goals to be able to add, make diffusion model accessible in other domains, like maybe 3D point clouds that we did at NeurIPS 2022. There was this diffusion language model that actually applied it to language model. They mapped words to some continuous space, and they use diffusion models in the latent space. And we also recently had this latent diffusion model that we applied to genome sequences. And this particular work got ACM Golden Bell Award last year. And we use this for representing the genome sequence of COVID data, which was really interesting. So if you don't have, I think I have, based on Yingjin, I have like 9 minutes based on the original.
Yes, you have 9 minutes, yes.
Okay, so I will skip this part, Denoising Diffusion GANs. I will go to this last part quickly. I think I can do it in like 5-6 minutes maybe. So the last one I want to talk about is called Genie, higher order denoising diffusion solvers, that was presented last year at NeurIPS 2022. So remember that I was telling you that this diffusion model, generative processing diffusion model, can be represented using stochastic differential equations, right? There is also a known ordinary differential equation, which we usually call probability for the ODE, that takes a deterministic mapping between noise and data distribution. And what happens is that basically you can train diffusion models, and at the sampling time, instead of solving this generative SDE, you can actually solve this deterministic ODE to generate samples. And it's also known that ODEs are usually easier to accelerate. You can use higher order ODE solvers to solve these ODEs, and as a result, you would need less number of sampling steps or function calls. So in this work, we want to come up with a higher order ODE solver. And here I'm going to show you a very simple ODE, generative ODE, that appears in diffusion model. So think of like you're solving this particular ODE. The easiest thing you can do is that at every step, you basically use first truncated Taylor method to approximate the function locally and update your sample using this like first order Taylor approximation of the function. So what you're doing here is that this is basically Euler method, right? What you're doing, you're just having a linear extrapolation. Given this point, you want to predict where the trajectory will go. You're just using a linear extrapolation. And you can imagine that if you have a high curvature locally in that area, your linear approximation will be poor. So you cannot take a very large step. You have to take a very small step to reduce the numerical error. But if you now use higher order, like second truncated Taylor method, you will have a better representation of the curvature, the generative like ODE trajectory. And because now you have a better representation of this function locally, you can actually take larger denoising step when you're solving these ODEs. So our basic idea is can we use these like higher order now terms to solve the generative ODEs with less number of calls? Like if we not can take large steps when we're solving ODEs, we will reduce the sampling time. It turns out that the first order Taylor method, it just needs this score function. Think of this as a score function. But the second order requires the derivative of the score function with respect to time. So this is a higher order score function actually. And our basic idea is that actually this quantity here has the same dimensionality as data space. So this is not a very complex, in terms of dimensionality, it's not very big. What we can do during training, like if we have a diffusion model, we can actually just use automatic differentiation to get this term. And after getting this term using automatic differentiation, we can just distill it to another tiny network to predict this term on top of a score function. So the basic idea is just to use the score network and add a tiny bit of head, like overhead to this, like we add just a little branch on the network to predict this term as well. And in order to train that, all we're going to do is we're going to use automatic differentiation and distill it to that score network. So this is a very basic idea. It just allows you now to have these higher order derivatives as well as the score function that you're predicting. And now that you have these derivatives, you can just solve the ODEs in lower number of steps. Remember, originally I showed you that the ultimate goal is to generate pictures of cats. So here we show you how you can use Genie to generate samples quickly on AFSQ data set. So when we compare Genie to other ODE-based solvers proposed for diffusion model, we see that actually Genie outperforms these models. This is up to, I think, NeurIPS 2022. Compared to other ODE solvers around that time, Genie can outperform them in lower number of functional evaluations. So just before ending the talk, I want to say thank you to all my colleagues and interns, most of the interns who were behind these things. Of course, I couldn't do, none of these are just my individual work. This is the works that I discuss here are the result of a lot of collaboration with amazing co-workers. I want to say thank you to my boss, Jan Katz, other research leads such as me, you and Sonia, and my collaborators, Karsten, Whaley, Yogesh, Sungjun, Jamin, and Shalini, and also amazing interns that we had the opportunity to work with, Tim, Shahu, Jishin, and Jarul, who did some of the works that I discussed here. So this is the end, and I will be happy to take more questions if there are any.
Yeah, thank you, Arash, for the great talk. Okay, so I think we have 2 to 3 minutes to open for questions. Okay, so if you have questions, you can raise your hand, or you can basically type your question into the chat. Okay. So maybe let me start and just allow people to type on think about their questions. Okay. So yeah. Okay. So you mentioned about these interesting 3 sort of like properties that you want this model to satisfy, right? And indeed, you have these kind of say diffusion kind of GAN kind of things that try to push towards that. Can you comment a little bit about, let's say, the state of the art right now, that whether you think that these sort of say 3 things has really been achieved, or there are still ways to go?
I think so. Diffusion models, I think the ultimate dream is to be able to build, interactive real-time applications with it. I think there's still a lot of work to go with them and to overcome that. There are some nice works, like, as I was saying, Chainlink Meng's work on like accelerating latent diffusion models that went down to 2 steps. I think those are still, they're very nice. I'm not sure if they enable still real time necessarily, like applications. The problem is that even if we can reduce it to like 2 steps, these networks are still very big. The complexity of these mappings is really hard. It's very hard to get to a single step. I think there is really nice work happening in the domain, in this space. Like, one of the very nice things was, again, consistency models from our friend Yang Sang, who announced very recently. Is also very nice work that attacks this accelerating sampling from diffusion models. But I think the ultimate goal is to be able to get to 1 function call, and hopefully that function call is also light. It's not a very expensive function call.
All right. Yes. Okay. I have another question. Okay. So, yeah. I mean, compared with, let's say, the old things that you've done with this NVAE stuff, right? Yeah. So the things that we notice right now is essentially that if you scale up your node architecture to some big architecture to some degree, then more or less speaking, you get results that all look awesome. And you can see recently there is GAN efforts from Adobe people, right? Also, so that they are awesome. Okay, so what's your comment in general for, let's say, the future developments for generative modeling, given the fact that you see scaling up network architectures seems to be working quite well?
So to be honest, I was also a big believer in that space. Like, when I did NVAE, I was like, okay, no one really did this thing for VAEs. Let's see what would happen if we scale these things up, right? The problem is, in general, data distribution is especially like image dance, is highly complex and multimodal. So my view is, you have these islands of data, right, that are separated because of having all these different categories and stuff. So any moment you have this like continuous latent space that you're trying to map to this very complex data distribution, you need very high Lipschitz in your network, right? So my view is, it is so high that it's very hard to have one network to do this, right? And so the way GANs do this, GANs say, okay, I'm going to drop most of the modes and focus on a few of them that I can capture really well, and I will do that. The way VAEs do, they say, I'm not going to be able to give up on any more. So it's like setting up a tent. You set up a tent on all the islands, but then you have so many like these gaps in between them, right? So my view is that it's really challenging to come up with networks that will have enough expressivity to do this mapping. There's of course some like view that, oh, actually discrete variables can do this, like I think some work that was like VQVAE, for example. Maybe this is one of the reasons why discrete VQVAEs were very successful at this space. The way diffusion models tackle this is very different. Diffusion models say, okay, I will never learn that function end to end. I'm going to break this process into smaller pieces. You know, like when you have this, if you look at the generative ODE, you start from a continuous distribution and you map it to this like highly multimodal distribution. But when you're learning pieces of it. And each piece, actually, you don't need a very high Lipschitz constant to be able to represent that. So my view is that diffusion will have broken this process into simpler problems that are easier to represent. And that's why we actually end up using many functional calls to be able to solve it. But things are different. Latent space thing can be a bit smoother, and it helps us to reduce this complexity. But I feel it's going to be very tricky just by increasing the expressivity of the neural networks to solve this. And that's one of the reasons why diffusion models are successful, is because the problem that they're solving in each step with one network is actually much simpler than the end-to-end problem.
All right. Okay. So there's no other questions. And also in the interest of time, I think let's just close. And yeah, thanks a lot, Arash, for your great talk. And also thanks everyone for coming. So have a great day.
Thanks a lot.